The times and amplitude of tides at a locale are influenced by the alignment of the sun and moon, by the pattern of tides in the deep ocean, by the amphidromic systems of the oceans, and the shape of the coastline and nearshore bathymetry. Some shorelines experience a semi-diurnal tide, two nearly equal high and low tides each day. Other locations experience a diurnal tide, only one high and low tide each day. A mixed tide, two uneven tides a day, or one high and one low, is also possible. Tides vary on timescales ranging from hours to years due to a number of factors. To make accurate records, tide gauges at fixed stations measure the water level over time. Gauges ignore variations caused by waves with periods shorter than minutes. These data are compared to the reference level, usually called mean sea level. While tides are usually the largest source of short-term sea level fluctuations, sea levels are also subject to forces such as wind and barometric pressure changes, resulting in storm surges, especially in shallow seas and near coasts. Tidal phenomena are not limited to the oceans, but can occur in other systems whenever a gravitational field that varies in time and space is present. For example, the solid part of the Earth is affected by tides, though this is not as easily seen as the water tidal movements. Characteristics. Tide changes proceed via the following stages. Sea level rises over several hours, covering the intertidal zone, flood tide. The water rises to its highest level, reaching high tide. Sea level falls over several hours, revealing the intertidal zone, ebb tide. The water stops falling, reaching low tide. Tides produce oscillating currents known as tidal streams. The moment that the tidal current ceases is called slack water or slack tide. The tide then reverses direction and is said to be turning. Slack water usually occurs near high water and low water, but there are locations where the moments of slack tide differ significantly from those of high and low water. Tides are commonly semi-diurnal, or diurnal. The two high waters on a given day are typically not the same height. These are the higher high water and the lower high water in tide tables. Similarly, the two low waters each day are the higher low water and the lower low water. The daily inequality is not consistent and is generally small when the moon is over the equator. Tidal constituents. Tidal constituents are the net result of multiple influences impacting tidal changes over certain periods of time. Primary constituents include the Earth's rotation, the position of the Moon and Sun relative to the Earth, the Moon's altitude above the Earth's equator, and bathymetry. Variations with periods of less than half a day are called harmonic constituents. Conversely, cycles of days, months, or years are referred to as long-period constituents. The tidal forces affect the entire Earth, but the movement of the solid Earth is only centimeters. The atmosphere is much more fluid and compressible, so its surface moves kilometers, in the sense of the contour level of a particular low pressure in the outer atmosphere. Principal lunar semi-diurnal constituent. In most locations, the largest constituent is the principal lunar semi-diurnal, also known as the M2 tidal constituent. Its period is about 12 hours and 25.2 minutes, exactly half a tidal lunar day, which is the average time separating one lunar zenith from the next, and thus is the time required for the Earth to rotate once relative to the Moon. Simple tide clocks track this constituent. The lunar day is longer than the Earth day because the Moon orbits in the same direction the Earth spins. This is analogous to the minute hand on a watch crossing the hour hand at 1200 and then again at about 1:05 1/2. The Moon orbits the Earth in the same direction as the Earth rotates on its axis, so it takes slightly more than a day, about 24 hours and 50 minutes, for the Moon to return to the same location in the sky. During this time, it has passed overhead once and underfoot once, so in many places the period of strongest tidal forcing is the above mentioned, about 12 hours and 25 minutes. The moment of highest tide is not necessarily when the moon is nearest to zenith or nadir, but the period of the forcing still determines the time between high tides. Because the gravitational field created by the moon weakens with distance from the moon, it exerts a slightly stronger than average force on the side of the Earth facing the moon, and a slightly weaker force on the opposite side. The moon thus tends to stretch the Earth slightly along the line connecting the two bodies. The solid Earth deforms a bit, but ocean water, being fluid, is free to move much more in response to the tidal force, particularly horizontally. As the Earth rotates, the magnitude and direction of the tidal force at any particular point on the Earth's surface change constantly. Although the ocean never reaches equilibrium, there is never time for the fluid to catch up to the state it would eventually reach if the tidal force were constant. The changing tidal force nonetheless causes rhythmic changes in sea surface height. Semi-diurnal range differences when there are two high tides each day with different heights. The pattern is called a mixed semi-diurnal tide range variation. Springs and neaps. The semi-diurnal range varies in a 2-week cycle, approximately twice a month, around new moon and full moon when the sun, moon, and Earth form a line. The tidal force due to the sun reinforces that due to the moon. The tide's range is then at its maximum. This is called the spring tide. It is not named after the season, but, like that word, derives from the meaning jump, burst forth, rise, as in a natural spring. When the moon is at first quarter or third quarter, the sun and moon are separated by 90 degrees when viewed from the Earth, and the solar tidal force partially cancels the moon's. At these points in the lunar cycle, the tide's range is at its minimum. This is called the neap tide, or neaps. Neap is an Anglo-Saxon word meaning without the power, as in Ford Ganges nip. Spring tides result in high waters that are higher than average, low waters that are lower than average, slack water time that is shorter than average, and stronger tidal currents than average. Neaps result in less extreme tidal conditions. There is about a 7-day interval between springs and neaps. Spring tide. Sun and moon on the same side. Neap tide. Sun and moon at 90 degrees. Spring tide. Sun and moon at opposite sides. Neap tide. Sun and moon at 270 degrees. Spring tide. Sun and moon at the same side. Lunar altitude. The changing distance separating the moon and Earth also affects tide heights. When the moon is closest, at perigee, the range increases, and when it is at apogee, the range shrinks. Every 7.5 lunations, perigee coincides with either a new or full moon, causing perigean spring tides with the largest tidal range. Even at its most powerful, this force is still weak, causing tidal differences of inches at most. Bathymetry. The shape of the shoreline and the ocean floor changes the way that tides propagate, so there is no simple, general rule that predicts the time of high water from the moon's position in the sky. Coastal characteristics such as underwater bathymetry and coastline shape mean that individual location characteristics affect tide forecasting. Actual high water time and height may differ from model predictions due to the coastal morphology's effects on tidal flow. However, for a given location, the relationship between lunar altitude and the time of high or low tide is relatively constant and predictable, as is the time of high or low tide relative to other points on the same coast. For example, the high tide at Norfolk, Virginia, U.S., predictably occurs approximately 2.5 hours before the moon passes directly overhead. Land masses and ocean basins act as barriers against water moving freely around the globe, and their varied shapes and sizes affect the size of tidal frequencies. As a result, tidal patterns vary. For example, in the U.S., the East Coast has predominantly semi-diurnal tides, as do Europe's Atlantic coasts, while the West Coast predominantly has mixed tides. Other constituents. These include solar gravitational effects, the obliquity of the Earth's equator and rotational axis, the inclination of the plane of the lunar orbit and the elliptical shape of the Earth's orbit of the Sun. A compound tide results from the shallow water interaction of its two parent waves, phase and amplitude. Because the M2 tidal constituent dominates in most locations, the stage or phase of a tide, denoted by the time in hours after high water, is a useful concept. Tidal stage is also measured in degrees, with 360 degrees per tidal cycle. Lines of constant tidal phase are called cotidal lines, which are analogous to contour lines of constant altitude on topographical maps. Semi-diurnal and long phase constituents are measured from high water, diurnal from maximum flood tide. This and the discussion that follows is precisely true only for a single tidal constituent. For an ocean in the shape of a circular basin enclosed by a coastline, the cotidal lines point radially inward and must eventually meet at a common point, the amphidromic point. The amphidromic point is at once cotidal with high and low waters, which is satisfied by zero tidal motion. Tidal motion generally lessens moving away from continental coasts, so that crossing the cotidal lines are contours of constant amplitude which decrease to zero at the amphidromic point. For a semi-diurnal tide, the amphidromic point can be thought of roughly like the center of a clock face, with the hour hand pointing in the direction of the high water cotidal line, which is directly opposite the low water cotidal line. High water rotates about the amphidromic point once every 12 hours in the direction of rising cotidal lines, and away from ebbing cotidal lines. This rotation is generally clockwise in the southern hemisphere and counterclockwise in the northern hemisphere, and is caused by the Coriolis effect. The difference of cotidal phase from the phase of a reference tide is the epoch. The reference tide is the hypothetical constituent, equilibrium tide, on a landless Earth measured at 0 degrees longitude, the Greenwich meridian, in the North Atlantic, because the cotidal lines circulate counterclockwise around the amphidromic point. The high tide passes New York Harbor approximately an hour ahead of Norfolk Harbor. South of Cape Hatteras, the tidal forces are more complex, and cannot be predicted reliably based on the North Atlantic cotidal lines.